Example number 1 down here, we've got f of x equals 1 over x. What does that picture look like? So if we remember back from I think it was algebra 2, you guys probably did things like 1 over x. 1 over x looks like this and this. It has a horizontal asymptote at y equals 0, and it has a vertical asymptote at x equals 0. Okay, whenever there's a vertical asymptote, that happens when your denominator equals 0. Okay, so at x equals 0, there's a vertical asymptote. So the graph is discontinuous. You can say the graph or the function is discontinuous at x equals 0. But you can see that our function is continuous literally everywhere else, right? You don't have to pick up your pen all along here, and you don't have to pick up your pen all along here. So 1 over x is continuous everywhere except at x equals 0. Second one, this is a piecewise function. We talked about a minute ago that lines and parabolas are continuous everywhere on their domain. Now, this is a piecewise function, so there's kind of two parts to the domain. Our first part to the domain up here is x is less than or equal to 0. So that's going to be everything to the left of the y-axis. Let's go ahead and draw x plus 1, which is to the left of the y-axis. I'm going to draw that one in blue. X plus 1, y-intercept of 1. At that y-intercept, we've got the equal sign for that part of the domain, so you are going to fill in the circle. And then our slope is 1, so I'm just going to do down 1 and left 1. Boom, there it is. Okay, then the second half of the graph, let's do that in green. We've got x squared plus 1, that is a parabola, where instead of going through 0, 0, it's going to have the y-intercept of 1. So 0, 1 is going to be that bottom part of the parabola, the vertex. And this is x is greater than 0. So if x is greater than 0, at 0, 1, we are going to have an open circle from this portion of the graph, and then we parabola it up to the right. Okay. Since we know that x plus 1 is continuous on its domain and x plus 1 is continuous on its domain, really the only thing we have to check is at the switchover of the domains, is our function continuous? And you can tell that a couple of different ways. You can tell it because the left-hand side and the right-hand side match up right there. You could tell it by taking the limit as x approaches 0 from the left of x plus 1 and the limit as x approaches 0 from the right of x squared plus 1, and you would see that you would get 1 both times. So really you're just plugging in 0 into both of these guys and you get 1. So this function is continuous everywhere. Okay, last one over here, x squared plus 1 over x minus 1. Okay, if we set our denominator equal to 0, we end up with x equals 1 would make our denominator equal 0. And what that means is that you either have a whole or a vertical asymptote. So let's take the top of the fraction and factor that out. X squared minus 1 factors into x minus 1 times x plus 1. And since we have a matching factor on the bottom, that means that there is a whole at x equals 1, right? The piece that makes that denominator equal 0. So if there's a hole in the denominator, there's a hole in your function, that means that your graph is going to be continuous, O-U-S, everywhere except at x equals 1. Okay, your graph looks something like this. Alrighty. After this, we talk about what is the word discontinuous. Discontinuous just means not continuous. Now, there are discontinuities. See how this word is slightly different than this one. A discontinuity is a spot where your function is not continuous. So discontinuous means like in general it's not continuous. Discontinuity is like the actual spot. We have two types of those, removable and non-removable. Removable means that you could literally just put in 1 point or switch 1 point. Switch or add 1 point. And then that would make your function continuous. So let's go to removable. And that is going to be whenever you have a hole in the graph. Okay, so I'm going to draw on this. Here's a hole in the graph. If I add a point right there, now our function is continuous. No big deal. So we removed the discontinuity. Also, remember how when there's holes in the graphs, you end up with like a 0 over 0? And like we did on number 3, anytime there's a hole, there's a factor that you can cancel. You can cancel or remove the factor from your fraction. So if you can remove the factor, it is a removable discontinuity. Removable discontinuity. Okay, so anytime there is a hole, it's a removable discontinuity. Non-removable, well, let's take a look at the other options. Number 3 up here, we had a hole. If we just take this point and fill it in there, like erase it from here, fill it in there, it's continuous. Over here, hole, fill it in, continuous. The only other types we have are vertical asymptotes and jumps in the graph. Okay, so let's say we have a vertical asymptote. I'm basically going to just redraw these two pictures down below for non-removable. Okay, so non-removable, let's do a vertical asymptote. Vertical asymptotes are non-removable discontinuities because if we put a point, we will never actually be able to make the left side and the right side match up. For example, if we put a dot here, the left and the right side do not meet. It doesn't now make this graph continuous. So let's try and move it up. That's where those arrows are closer to each other. Move it up. Still doesn't meet. Move it up. Still doesn't meet. Move it up. Still doesn't meet. These arrows are getting closer and closer and closer, but they never actually touch, even if we put one spot in there. So vertical asymptotes are non-removable. Okay. Also, if you have a fraction for your actual function, let's say this is at x equals 2. If you have an actual function, this is like f of x, a non-removable discontinuity would have something that cannot be canceled, like x minus 2 could not be canceled because there's nothing to match it on the top. Okay. The other option is a jump discontinuity. So vertical asymptotes or jumps. If you have a jump in the graph, it is not continuous to start out with, but let's say we wanted to just fill in this hole. Well, fill it in. There's a problem here, and some of you guys talked about it the other day. This is now not a function because it doesn't pass the vertical line test. All right, so maybe you say, let's just get rid of this point and make it a hole and fill in this one instead. Well, there's still a jump, there's still a gap, so we can like move towards it, but then we have to pick up the pencil to move down here. Okay, jump discontinuities. The only ones I can really think of come from piecewise functions. Okay, and those show up whenever your domain changes, like when we switched from x is less than or equal to 0 to at x is greater than 0. We did not happen to have a jump in this problem, but that happens quite a bit. if this had just been x squared plus 2, this green piece would have been moved up and there would have been a jump in between the left side and the right side.